Today we'll discuss about filters. Filtering forms a very important activity in analog signal processing. We are trying to improve the signal to noise ratio of most of our signals, analog signals, after it comes from the transducer. So this is the first step towards improving signal to noise ratio, and we need different kinds of filters. And one of the most important building blocks in filters is called universal active filter. So we are going to discuss that circuit today and use this circuit in understanding a variety of important filtering functions. We've chosen this circuit mainly because this is the standard building block which is adopted in present day continuous time filtering, whether this is translated to switched capacitor or retained in continuous time form, okay, depends upon the context of IC utility in present day VLSI. So let us therefore discuss this circuit. Why is it called universal and what is so good about this filter? So if Vi is applied here, and if let us say V01 is the output here, this V01 gets integrated and appears as minus V01 by SCR here, okay, once integrated, and second time integrated it gives you plus V01 by SCR square. So that is why from a basic input we are trying to get the other states, once integrated and twice integrated state, and so that we can set up a second order differential equation. That's all it does. So we are adding these to the output as minus V01 by SCR square coming from this, and this one is once integrated, so this appears as a modifying factor SCR2 with plus sign, one more inversion. This Q is the modifying factor for its coefficient, and then the input gets added as H0 into Vi here. Finally, this is inverting the whole thing and making it appear here as minus V01 by SCR cube, okay, plus H0 into Vi. So now collecting the coefficient of V01, we get V01 by Vi as SCR square by SCR square plus SCR by Q plus 1 into H. This is called high pass filter or second order high pass filter. If we have first order filter, which is just using one R and C, we can get first order low pass, okay, or first order high pass. And along with that, we can get now a second order high pass. That means basically we can design any nth order filter as a cascade of one first order and any number of second order filter blocks. That's why understanding first order filter design and second order filter design almost completes the nth order filter design. You can, by combination of these two orders, we can get any higher order. So now this particular output of the high pass is given to this, and it becomes band pass output. So here V02 is going to be band pass, H0 into SCR. Once again it gets integrated with high pass gets integrated, we get band pass filter. And V03 by Vi is low pass. One more integration. The denominator remains the same. So these are the outputs at these various points, V03. And if you take V04, we can show that V04 by Vi is another important second order function which is called all pass or band stop, okay, or band elimination. All pass is a combination of high pass, low pass and band pass, such that the location of the zero is a mirror image of the location of the poles. That way, all pass filter can be designed by simply summing up these three outputs of the low pass, high pass and band pass appropriately. So for that matter, any second order filter which is stable can be synthesized by using the outputs of these various op amps and adding them or subtracting them appropriately. So an all pass filter, for example, which has constant magnitude and variable phase shift can be generated using this. Okay. Now, this output of band stop is 1 plus S squared by omega naught squared by 1 plus S by omega naught cube. So S squared. Where omega naught is 1 over RC, it can be changed by changing R and C, and Q is the quality factor. Okay. Or the poles of the system. Now that you have understood the circuit which can give us a general second order system, which is called universal active filter because of its ability to simulate any second order with poles always on the electron plane and zeros anywhere on the S plane. And therefore, such transfer function, once it is created, we are going to be able to study the various outputs like low pass filter, band pass filter, and band stop filter, and high pass filter, etc. Let us first consider the low pass filter. So it has only two poles at a point on the electron plane. If it is on the real axis, negative real axis, okay, the Q is less than or equal to half. If the Q is greater than half, okay, the poles split into complex conjugate pairs. You can see that the solution of this is S by omega naught equal to minus 1 over 2Q plus or minus root of 1 minus 1 by 4Q square. So if Q is, so the poles of the system will be on the negative half of the S plane, and we can solve this by equating it to 0, and we can see the roots are 1 by 2Q or omega naught by 2Q plus or minus omega naught into 1 minus 1 by 4Q square. So for Q less than half, which is called the Q equal to half is called the critical damping. Damped is for Q greater than half, in which case there is ringing at the natural frequency times square root of 1 minus 1 by 4Q squared. This becomes J here. Okay, for Q greater than half, right? The pair has complex conjugate, roots. Whereas Q less than half, it is on the negative real axis. It is overdamped. It is exponential. Okay. And the ringing frequency is given by this. When Q is very high, it is almost equal to the natural frequency of the system. So it starts ringing very near to the natural frequency when Q is very high, and the number of such rings which are visible will be equal to the value of Q. Okay. So this we can see by subjecting this low pass filter to a step response and seeing when it is ringing, okay, and how many such peaks are visible. And in the frequency response characteristic, the magnitude will show a peak when the Q is very high, and it peaks very nearly at the resonance frequency, okay, for high Q, and the value of the peak is directly proportional to Q for high Q. Okay. This is the phase response for the same low pass filter, and the phase response can be seen to have maximum sensitivity or variation of phase with respect to frequency variation is the highest at omega equal to omega naught, and the value of that, which is nothing but delta phi, if this is phi, by delta omega. You can prove that it is highest at omega naught and is having a value of 2q by omega naught. And that is why phase detectors are used for tuning filters. Right? Because phase detector output is the one that is very sensitive to variation in frequency. Okay? And therefore, it is always that you have to use a parameter which varies maximum. Okay? And that is very conveniently occurring around omega naught, the pole frequency of the system, and therefore we can tune most of the filters by using this information about phase. So we'll later on see how phase detector can be used for tuning, okay, in self-tuned filters or phase lock loops. Okay. It is necessary for you to apply a sine wave and obtain the frequency response is magnitude and phase characteristic and observe this phenomena. And for notch filter, the magnitude response will be exactly looking like this, and this notch occurs at omega equal to omega naught. And higher the Q, sharper is going to be the notch. And therefore, it can be very conveniently used to reject, for example, 50 Hz power line frequency. Right? So you can reject the unwanted frequency, clock frequency or power line frequency, which is normally the most irritating thing in signals. So you use a notch filter. And an all-pass filter which has the poles and zeros as mirror images. Right? So this will be the pole remains the same as before, and in the zero you have high pass, then band pass with negative sign, and low pass. So this gives you a constant magnitude characteristic. However, the phase varies from 0 to 360 degrees. Okay, 0 to pi is caused by one pair of poles, and further phase shift of another additional pi can occur due to the 0 in the numerator. So please plot the frequency characteristic, both magnitude and phase, and also obtain the transient response. Apply a square wave around the natural frequency of the system and see that the notch filter output is nothing but the harmonic of the square wave, and band pass filter output is nothing but the fundamental. Therefore, this system can be used also for as a spectrum analyzer for a periodic waveform, where the fundamental, okay, is picked up at the band pass filter output, and the rest of the harmonics occur at the band stop filter output.